welcome to the deep dive. Ever looked up on a clear, dark night and maybe, just maybe, spotted this faint, fuzzy patch of light? High chance you were actually looking at the Andromeda Galaxy,
Yeah.
M31.
Yeah, our closest really big galactic neighbor. A spiral galaxy, much like our own Milky Way in many ways.
It's huge, right? Something like 65, 70,000 light years across
Mm,
and about 2.5 million light years away.
exactly.
Yeah.
It's basically the biggest thing in our local group of galaxies.
So today, we're doing a deep dive into Andromeda. We want to unpack its story.
That's the plan. How did it form? What's its evolution look like over, well, billions of years? What's it made of?
And we'll be leaning on some pretty recent science, especially findings from the Gaia space mission. We've got a source here, Perryman Gaia 083.pdf, that gives us a lot to chew on.
It really does. It helps piece together the picture of this, galactic sibling.
Okay, so it's big, it's relatively close. But beyond just, wow, another galaxy, why focus on Andromeda? Why is it important for us?
Well, think of it like this. Studying Andromeda gives us perspective on ourselves, on the Milky Way.
How so?
Because it's so similar in mass and type, the ways Andromeda formed and changed over time, they probably echo our own galaxy's history quite a bit.
Ah, okay. So understanding its story helps us understand our story. And maybe our future.
Precisely. It's like looking at a slightly different version of ourselves. A cosmic comparison.
Got it. Okay, let's jump into that story then. How far back do we need to go for Andromeda's birth?
We're talking way back. The current thinking, supported by work like David and others in 2012, suggests Andromeda started forming around 10 billion years ago.
10 billion. Wow. And how did that happen? Just poof, a galaxy appears.
Not quite. More like a cosmic construction project. It likely came together through collisions and mergers of smaller, sort of proto-galaxies, baby galaxies, you could say.
Right, a bunch of smaller things smashing together.
Exactly. And that process, that chaotic merging, would have triggered a massive wave of star formation, a huge burst.
And that's when the main parts formed. The disk, the halo.
That seems to be when the bulk of its halo, that big diffuse sphere of older stars around it, and the initial extended disk really got established. A pretty dramatic beginning.
So not exactly a quiet childhood. Did things calm down after that initial phase?
Well, yes and no. It wasn't constant chaos, but there were definitely more major events later on.
Like what? I think I read something about a run-in with another nearby galaxy.
You're probably thinking of the Triangulum galaxy M33. It seems Andromeda had a pretty close pass with M33 somewhere between 2 and 4 billion years ago.
A close pass, not a full collision.
Yeah, more like a near miss, gravitationally speaking. But even that had big effects.
Such as?
It likely stirred things up enough to trigger more bursts of star formation in Andromeda's disk. And you can even see signs of disturbance in M33's outer disk, possibly from that interaction.
Amazing. The gravitational dance between galaxies. And what about smaller interactions? Did Andromeda gobble up any smaller galaxies?
Oh, almost certainly. That's part of how big galaxies grow. We see
Yeah.
evidence of this, like the giant stellar stream in Andromeda's halo.
A stellar stream. Like a river of stars.
Kind of, yeah. A long looping trail of stars, richer in heavier elements or metals, as astronomers say, than the typical halo stars. Research, like Ibada's back in 2001, suggests this stream was likely created when Andromeda interacted with, or maybe even tore apart, a satellite galaxy, possibly M32 or M110, its close companions.
So remnants of past meals, basically.
You could put it that way. And there's evidence for even more recent activity, too. Maybe around 100 million years ago, another merger event might have happened.
100 million. That's practically yesterday in cosmic terms. What did that do?
Well, one leading idea is that this more recent merger could explain the weird counter-rotating gas disk we see right in Andromeda's center. Gas spinning the opposite way to the main rotation.
Huh, that is weird.
And it probably added a sprinkle of relatively young stars to the central region as well. So, yeah, a history of bumps, near misses, and outright mergers.
Okay, so that's the history. Let's talk about the structure now. What does Andromeda look like up close? Does it look just like the Milky Way?
It's got the classic spiral galaxy look, definitely. Beautiful, prominent spiral arms. They're actually a bit more tightly wound than ours, but also more widely spaced apart.
And those arms are where the action is, star formation.
Absolutely. They're studded with those bright pinkish clouds called HII regions. Those are stellar nurseries, basically giant clouds of gas being lit up by hot newborn stars.
Okay, classic spiral. What about the very center, the core?
Right in the heart of it, there's a very dense, compact cluster of stars, packed really tightly together.
And presumably, a supermassive black hole, like ours.
You bet. And Andromeda's is a monster. Estimates put it somewhere between 100 and 200 million times the mass of our sun, significantly bigger than the Milky Way's central black hole.
Whoa! 1 to 200 million, that's enormous. Does a black hole that big sort of dominate the center?
It certainly has a huge gravitational influence on the stars whipping around it. It doesn't directly make stars, but its gravity definitely shapes the environment in the galactic core.
Affecting how gas moves around, maybe.
Exactly. It influences the dynamics of gas and dust, which plays into where and how stars might form nearby. And that counter-rotating gas disk we mentioned. Its existence might be linked to the black hole and past merger events feeding gas into the center.
Okay. And surrounding the main disk and the bulge, there's the halo. Right. You mentioned that formed early on. How does it compare to the Milky Way's halo?
It's pretty similar in concept, a large, roughly spherical region containing much older stars. And like our halo, these stars are generally metal-poor, meaning they have fewer heavy elements than stars like our sun.
Which tells us they formed early, before the galaxy had time to enrich itself with metals from later generations of stars.
Precisely. And what's interesting in Andromeda and in our galaxy too is that as you go further out into the halo, the stars tend to become even more metal-poor, on average.
Really? Why is that?
It fits nicely with the idea that galaxies build up hierarchically. The outer halo might be composed more of the remnants of very old, very small, very metal-poor galaxies that merged early on.
Okay, that makes sense. Now, we've been throwing around distances like 2.5 million light years. How on earth do scientists measure something that far away?
Yeah, it's a great question. It's definitely not using a tape measure. We rely on something called standard candles.
Standard candles?
Yeah.
Like objects with a known brightness.
Exactly. If you know how intrinsically bright something is its wattage, like a light bulb, then you can figure out how far away it is by measuring how faint it appears to us.
Okay, so what are the standard candles for Andromeda?
There are a few key ones. Cepheid variable stars are classics. These stars pulsate, and crucially, the time it takes them to pulsate is directly linked to their true brightness. Measure the period, know the brightness, measure the faintness, get the distance.
Clever. Any others?
Yep. We can also use certain types of eclipsing binary stars. Watching how their light dims as one star passes in front of the other lets us calculate their physical properties very precisely, including their distance. And another important one is looking at stars right at the tip of the red giant branch phase in their evolution. They reach a very consistent peak brightness before they fade.
And do these different methods agree?
Remarkably well, actually. They all point to a distance around 778 plus or minus maybe 34,000 kiloparsecs, which is roughly 2.5 million light years. It gives us confidence in the number.
That's reassuring. And that distance, our source mentions, means the apparent shift in position, the parallax, is tiny, about 1.3 microarcseconds.
Tiny indeed. And that's a really important point regarding Gaia.
Because Gaia measures parallax to get distances, but it can't quite manage that for individual stars in Andromeda.
Exactly. Gaia is incredible for mapping our own Milky Way in 3D by measuring parallax for billions of stars. But Andromeda is just too far away for Gaia to get reliable parallax measurements for its individual stars. The angles are just too small to measure accurately enough.
Ah, okay. So Gaia can't map Andromeda in the same way it maps the Milky Way, but it can still study it. You mentioned the Gaia Andromeda Photometric Survey, GAPS.
Right. Just because Gaia can't measure the parallax of individual M31 stars doesn't mean it can't provide other incredibly valuable data, and GAPS is a perfect example.
So what was the idea behind GAPS?
Well, first, you need to understand how Gaia data comes out. It's not one single data dump. The mission releases data in stages DR1, DR2, DR3 with DR4 planned.
Getting bigger and better each time.
Pretty much. More stars, better accuracy, more types of data. This staged approach lets scientists jump in early, work with the data, find issues, provide feedback, and helps improve the final products. It's iterative.
Okay, so DR1 was 2016, DR2 in 2018, DR3 was June 2022.
Correct. And DR4 is expected maybe around 2025 or so. A key thing that's been growing with each release is the amount of epoch photometry.
Epoch photometry, meaning measurements of a star's brightness taken at different times.
Exactly. Time series data. Crucial for studying anything that changes, especially variable stars. DR1 had maybe 3,000 variables with this data. DR2 jumped to 500,000. DR3 hit about 10 million.
Wow. And the goal for DR4 is?
To have time series data for basically everything Gaia sees. Now, GAPS within DR3 was kind of a specific test case for this.
A test case. How so?
The idea was, okay, before we release epoch photometry for all stars, let's focus on one specific interesting field, process it fully, and see what we learn. Get user feedback, a sort of pilot program.
And they picked the Andromeda field for this pilot. Why there?
It was a really smart choice for several reasons. First, the way Gaia scans the sky means that field gets a wide range of observations. Some parts scanned only maybe 10 times, others up to nearly 60 times during the DR3 period.
So you can test how the number of data points affects the results.
Precisely. Second, the field contains everything from sparse regions far from Andromeda to its incredibly crowded central bulge and spiral arms.
Ah, perfect for testing how well Gaia handles crowding, where stars appear blended together.
Exactly right. Crowding is a major challenge. And third, a big 5.5-degree circle around Andromeda naturally includes tons of foreground stars that are actually in our own Milky Way.
Which is useful because...
Because those foreground stars give you a nice, well-populated Hertzsprung-Russell diagram, that plot of star brightness versus color. You can use those Milky Way stars for calibration and comparison.
Makes sense, a diverse test field. So what did the GKPS dataset actually look like in the end?
It was pretty substantial. Epoch photometry time series brightness measurements in Gaia's three main filters, G, BP, and RP, for over 1.2 million sources.
1.2 million. And how many measurements per star, typically?
Most had somewhere between 30 and 45 observations over the DR3 time span. About 15% had even more, over 50.
But fewer in the very center you mentioned, because of crowding.
Yeah, that was expected. In the most packed regions of M31, it's just really hard to separate the light from individual stars, especially in the BP and RP bands, which use slightly wider fields of view. But the processing is getting better, so future releases should improve on this.
Still, a huge amount of data. Did just the basic colors of the stars reveal anything interesting?
Absolutely. If you look at the average color using the BP minus RP filter brightness difference, you see a clear pattern. Away from Andromeda itself, the average color in the field is about 1.4 magnitudes.
Okay, sort of reddish on average.
Right, but if you zoom in on the parts of the GPS field that cover Andromeda's spiral arms, the average color shifts bluer to about 1.0 magnitude.
Indicating younger, hotter stars in the arms.
Exactly. It matches what we expect. Those spiral arms are where more active star formation is happening, so you have more of those massive hot blue stars lighting things up.
Cool. Okay, so GPS provided all this time series data. How did the researchers like Evans and the team mentioned in our source actually use it to find stars that vary in brightness?
They came up with a neat statistical tool, a variability index they called R.
R4.
They don't explicitly say maybe residual, but essentially it quantifies how much a star's individual brightness measurements deviate from its average brightness across all three filters, G, BP, RP.
That looks for scatter beyond what you'd expect from measurement errors alone.
Exactly. They used a technique called principal component analysis, which is good at finding the dominant patterns of variation in complex data to combine the information from the three filters and create this single R index for each star. A high R value means the star is likely variable.
Okay, and then they could plot this R value on the Hertzsprung-Russell diagram.
Yep. They color-coded the HR diagram based on the R index. So regions with lots of variable stars would light up in certain colors. It gives you a great visual map of where different types of variability happen in terms of stellar temperature and luminosity.
But the specific diagram in the source paper, that wasn't actually showing Andromeda stars.
Yeah. Correct. That's important. The example figure they showed was specifically limited to stars with really good parallax measurements less than 10% error. That means they're almost certainly foreground stars in our own Milky Way, not in M31.
Okay, so it's showing variability patterns for Milky Way stars in that direction.
Precisely. And it was showing sort of average variability levels in different zones of the HR diagram, not necessarily every single variable star plotted individually, but it beautifully illustrated the technique. And importantly, many of the stars flagged by this R-index method were also identified as variables by the main separate Gaia pipeline for variability analysis in DR3.
So the methods confirmed each other, which builds confidence.
Definitely.
So what kind of variable stars did this R-index map reveal? Were there specific hotspots on the HR diagram?
Oh yeah, several distinct regions lit up. First, down below the main sequence, they found highly variable blue objects identified as cataclysmic variables.
Those are binary systems, right?
Yeah.
White dwarf pulling stuff off a companion.
Exactly, often leading to dramatic outbursts. Then, on the main sequence itself, they saw the classic instability strip.
For stars naturally pulsate.
Right. Populated by Delta Scuti, stars faster pulsators, and slightly fainter, the Gamma Doradus stars, which pulsate more slowly due to different physical mechanisms, G modes versus P modes.
Okay. What else?
Over towards the giant branch, there was a clump showing strong variability. These were identified as RS-Canem venaticorum type variables.
RSCVN. Those are often active binaries too, aren't they? Star spots.
Yep, often binary systems with lots of magnetic activity, star spots causing brightness changes as the stars rotate. Then, way over in the cool red giant region,
Let me guess. Long period variables.
you got it. That area was dominated by things like Mira variables, those famous large amplitude, long period pulsating red giants, but also semi-regular variables, which are less predictable, and OSARGs.
Those sorts. What's that?
Stands for OGLE, small amplitude red giants. Basically, red giants with more subtle, lower amplitude variations.
Huh, okay. Any surprises?
Well, they noted a couple of less well-understood features. A faint ridge of variability kind of in the middle of the main sequence, which was a bit unexpected, though maybe hinted at before, and another ridge at the very top, the bright end of the main sequence.
And what was causing the variability there?
Seems to be a mix of things up there. Many are linked to binary star interactions, eclipses, tidal distortions, that kind of thing.
So it sounds like GAPS, even focusing mostly on foreground stars for this variability index, already gave a really rich picture of the variable star zoo in that direction.
Absolutely. It really showcased the power of having this time domain data for millions of stars. And as our source emphasizes, this is really just scratching the surface.
The analysis isn't finished by any means.
Not at all. Properly characterizing all these variables identified by Gaia in the GAPS field, figuring out which ones might actually be in Andromeda despite the distance, and generally digging deeper into everything Gaia saw in M31. That's a huge amount of work still to be done by the community. GAPS was a vital proof of concept.
All right, so wrapping this up, our deep dive today has really painted a picture of Andromeda as this dynamic galaxy shaped by massive mergers early on, close calls with neighbors like M33, and ongoing interactions.
Yeah, with its giant black hole, its distinct spiral arms, its ancient halo, and those telltale stellar streams hinting at its past.
And cutting-edge tools like the Gaia mission, through specific efforts like GAPS, are giving us unprecedented data like time series brightness for millions of stars to probe its structure in the stars within and in front of it.
Exactly. Even if Gaia can't measure the distance to Andromeda's stars directly via parallax, the photometry, the colors, the variability data, it's all incredibly valuable.
And understanding Andromeda, its history and makeup, isn't just about satisfying curiosity about our neighbor, is it?
No, absolutely not. It's fundamental to understanding how galaxies like ours form and evolve across the universe. Studying Andromeda helps us refine our models, test our theories, and ultimately understand our own Milky Way's place in the cosmos.
It gives us context for our own galactic home.
Precisely. And, looking even further ahead, studying Andromeda might even give us clues about our very distant future.
You mean the collision, the eventual merger between the Milky Way and Andromeda?
That's the one. It's billions of years away, but understanding Andromeda now helps us model what that incredible cosmic event might look like when it eventually happens. A fascinating, if slightly unsettling thought to end on.
Definitely something to ponder next time you look up that faint smudge in the night sky. Thanks for joining us for this deep dive. We'll see you next time.